Thank you, Rama. Meaning that it cannot be stretched. This length is 130. So the length of the string 130 centimeter. I'm coming in. All right. Let me go back to the question. I had a message. So the length is 130, whose upper end is fixed to the ceiling. The sphere is made to describe a horizontal circle of radius 50 centimeter. So the radius of the circle is 50 centimeter. Calculate the period of revolution and what is the tension in the string. So we are calculating for the period and the tension in the string. Okay. Now it is suspended to a ceiling. And there's a ceiling. There's a string. This is the sphere. Now it is tilted to create a horizontal circle. It means that it has to be displaced and then be given an angle to describe the horizontal circling. So each part will look like this. And this is what they mean. Okay. We are given the radius, which is 50 of the circle formed. Then the length of the string, 130. Theta was not given. But the fact that it will perform a horizontal circling means that it should be displaced at an angle so that it moves this way. This is what they mean by, excuse me, this is what they mean by horizontal circling. Okay. So how do we determine the period? Okay. And how do we determine the tension in the string? How do we determine the tension in the string? And one basic relation we learned from conical pendulum is that T cos theta, horizontal component, is always balanced by the weight, mg. Then T sine theta is what provides the centripetal force. Another basic relation we always apply is the radius is equal to the length times sine of the angle theta. So these are the basic relations we are going to use to determine, okay. This question requires of the period. First, let's see if we can determine the tension, okay. Then we determine what follows. Now, we have the length. we have the radius of the circle. And so we can find the angle of inclination, which would help us find the tension. So using R is equal to L sine theta is equal to R, which is the radius. What's the length? The radius is 50 divided by the length, which is 130. Therefore, theta is equal to the sine inverse of whatever we have here, 5 on 13. Please, what's the sine inverse of 5 on 13?
22.62.
So 22.62 degrees. And once we have theta, we can easily find the period, the tension. So T is equal to the mass, which is, we quickly change the gram, 200 gram to kilogram, and that will be 0.2. So 0.2 times 10 meter per second squared divided by force of 22.62. Somebody may ask, why are we quickly converting the mass from gram to kilogram? It is because we'll be using, the question never gave us G, but if it's not given, we are always using 10 meter per second squared. Okay, so if you are using 10 meter per second squared, then you need to convert all other units to SI. The reason for which they are really changing from gram to kilogram. So Charlotte, what is T? Hello class, what is T? 2 divided by cos 22.62.
2.17.
Come again.
2.17 Newton.
That's the tension. Period. Period. I'm assuming I have no idea of the formula, because if you can't memorize formula, that it does not mean you shouldn't be able to solve this. To determine period, when I don't know any relation, I'll equate T sine theta, which is equal to the centripetal force, to M omega squared R. Okay, so here I'm switching from mv squared over R to M omega squared R. In case I have no, hello.
Sir, please, I would like to, you see for the tension,
Yes.
we had 2.17 newtons.
Yes.
So say for the tension, we had 1.9 newtons. Is it also correct?
No, you should get the same figure. Herbert,
Yeah.
is that you?
Yes, sir.
Yes, this is what I realized. I realized you use this formula. T is equal to 2 pi root of L over G, which is wrong. This is the formula for the period of oscillation of a simple pendulum.
Okay.
This is a different thing altogether. It's not about conical pendulum. That is why when you submitted your work, I saw it, but I didn't want to mark because I will mark you down in all. So I just felt, okay, we'll be meeting. I'll address it for you to understand. Is that okay?
Okay, sir.
So
Yes,
you
sir.
see this formula when we start SHM. It's a different thing. Is that okay?
Okay, sir.
All right. So T, there's a tension. Now, I can get the period from omega. So what I want to do is to make omega squared the subject. I have T sine theta over MR. This is because I have every member of this family. I have T, I have theta, I have M and R, so I can find omega. Therefore, T, which is
Mr. Dia,
hello,
please, so in the second instance, the T here is time or extension.
T, Charlotte, once this T is from T cos theta, T sine theta, it means it is tension. When it comes to the period, I'll use small letter t to create the distinction, right?
Yes, please.
So
Thank
2.17 times sine of 22.62 over the mass 0.2 times radius 0.5. So calculate and then give me whatever you have for this. Sine 22.62 times 2.17 divided by the denominator. Please, let's hurry up in our calculation. Everybody must get involved so that we utilize time properly.
Mr. Dia, please, can you shift your camera to the right a bit? Thank you.
The rest of you should not be spectators. Get involved. Let's utilize the time.
Please, I had 8.35.
For everything,
Yes, please.
so omega is equal to the square root of 8.35. What is the square root of 8.35?
2.89.
2.89.
89.
I must speak up.
Accuracy.
So if omega is 2.89, then we know omega to be equal to 2 pi over the period capital T. Because tension is capital T, let's change this T to small t, even though we have small t too. Therefore, you equate 2 pi over this T to 2.89 and make T the subject. T being made as the subject here will be equal to 2 pi over 2.89. So calculate it for me quickly. Pi is 3.142. So multiply 3.142 by 2, divide that by
2.17.
come again.
2.17.
Okay. So we have 2.17 approximately that. So the period is 2.17 seconds. That's all. Okay. Now, if you happen to memorize the formula for the period, capital T, which is, I think, 2 pi root of L cos theta over J. It must give you the same value. But I'm doing this in case you are not able to memorize this, that is how to come by the formula for or an expression for the period. Please, is that okay? Any question? No question. Let's move on to the question. Can I adjust the screen? I'm moving on to question
No,
2.
please.
Okay, Charlotte, hurry up.
Yes, please.
Can I continue?
No, please.
Yeah, no, please, no, please.
Please, I'm done.
Okay.
Thank you.
I think the question 2 was a bit stubborn than question 1. And I can count a lot of you who were flogged by the question. Do I mention names?
No,
Please.
Okay. Charlotte, do I mention names?
Oh, Mr. Dear.
But I'm just asking a question. As for the guys, the gentlemen, a lot of you never tasted the question at all. Only Herbert tasted. And it was bitter. Carl. Okay, so question 2. Let's go through the question. Question 2, a string of length 1 meter. The length of the string 1 meter is fixed at one end and carries a mass of 100 grams. So the mass of the sphere 100 G. At the other end, the string makes 2 per revolutions per second. So if 2 per revolutions per second, then this is angular velocity. 2 over pi. Around a vertical axis. Around a vertical, hello.
So please, is it not 2 over pi rad per second?
It's revolutions per second. Rev per
Okay.
second. Around a vertical axis, passing through its end. Calculate I, A, the angle of inclination. And then tension, and then the linear velocity. When gravity this time is given as 9.8 meter per second squared. So you look at the actors and then the actresses of this movie. The length is in meter, SI unit, mass, gram. So quickly, this must be changed to 0.1 kilogram. This is 2 over pi revolution per second. So this, when you change this to radian per second, it will be 2 over pi times 2 pi, which will give you 4 radian per second. So straight away, we change this to 4 radian per second. Then we have everything in SI units. All is well. We are to determine the angle of inclination first. What we know about angle of inclination? 3 things. 1, R is equal to L sine theta. Will this help? We don't know R. We don't know theta. We have L. We should move on. We also have, at least we have V is equal to omega R. We don't have V directly. We have R. We have omega. We don't have R. Then we have V is equal to V squared is equal to RG times tan theta. But this should ring a bell. If V is equal to omega R and V squared, or even V is equal to the square root of this, then if I substitute this for V, I can have omega R is equal to the square root of RG times tan theta, so that omega R all squared will be equal to RG times this. If you open this further, you have omega squared R squared is equal to RG times tan theta. This R can reduce the R here. Okay. This R can cancel out. So we have omega squared R G times tan theta. Right? Look through. Let's look through to see if this would help us. We have G, we have omega. We don't have R directly. Okay. Another way. You see, we also have R. Look at the substitution. We also have R equal to L sine theta. So quickly, I can substitute L sine theta for R, and this is G sine theta, tan theta is sine theta over cos theta. If I multiply through by 1 over sine theta, I can eliminate sine theta so that this and this will cancel. This and this will cancel. Omega squared L is therefore equal to J over cos theta. It means that once you have omega, L, and G, you can find theta. So here you must be a bit, have that knowledge to look around, see how best you can simplify things. Another way out is this. Another way to do the same thing is this. T cos theta is equal to mg. T sine theta is equal to, instead of mv squared, I'll use m omega squared r. because I have omega. So if I divide equation 2 by 1, okay, left hand side I have t sine theta over t cos theta, which is equal to m omega squared r over mg. And so sine theta over cos theta, I have tan theta, is equal to omega squared r over g. Omega, we have it. R we can express R in terms of theta and L. G, we have it. So because R is equal to L sine theta, we have tan theta is equal to omega squared times L sine theta, all on G. At least we all understand that tan theta is sine theta over cos theta. And so when you divide through by sine theta or multiply through by 1 over sine theta, this and this will cancel, this and this will cancel. And so we have 1 over cos theta equal to L omega squared over G. Therefore, cos theta would be equal to G over L omega squared. Amma, Charlotte.
Yeah.
And
Are you seeing something?
A lot
Yeah.
of things.
So you must be able to think through and play around. Just, okay, try substituting this into this, see what you can get and all that. So G, which is 9.8 over L is 1 times omega is 4, so 16. So divide 9.8 by 16. What's the answer? It should be 50 something.
Yeah,
Hello, I'm
please,
waiting.
thank you so much.
Pardon?
I was about to tell you to please move the camera down, but you did.
I want the final answer.
52.2.
So theta is 52.2. And once you have theta, you are true. The next one is to find the tension. So once you have theta, equation 1, equation 2, you are good to go. You are good to go. The third question is that the linear velocity. Linear velocity, once we have theta, this can do, this can also do, and you get the same results. You get the same results. So class, this is it. Herbert. Herbert. Okay. Can I
Miss
clean
Davia.
it? Hello.
So please, I used W's omega squared is equal to G tan theta over R, and I got theta to be 58.
Let me write. You said you use omega.
No, omega squared
Mhm.
is equal to G tan theta over R.
G times theta. Tan
No,
theta. I
tan
think it's
yeah,
tan theta.
yes, over
Yes.
R.
Yes.
Then I
You
got
need to-
theta to be 58.
You got theta to be 58.
Yes, please.
Let's see. This is 16. You see, did you take R to be 1?
Yes, please.
That's your problem.
Oh, okay. Thank you.
R is L sine theta. So until you have found theta, even finding R is a problem. Please, that also reminds me, R will not be equal to L in this case. For conical pendulum, R is not equal to L. It is when the object revolves, when the angle to the horizontal, the string makes with the horizontal is 0. So I demonstrated this last time. If I have this object, flat circling or revolution is this. Here, I'm revolving, I'm rotating this, the object, so that this angle, the string makes with the horizontal is 0. Here, the radius is equal to the length. But this is conical pendulum, whether hanged on a ceiling or something. Okay, this is conical pendulum. Okay, so for conical pendulum, this is how it is. There is a vertical. The string makes an angle theta with the vertical. This is the sphere. When the sphere rotates, the shape describes a cone, hence conical pendulum. This is a conical pendulum. This is not the same as rotating an object flat along the horizontal. So for conical pendulum, this is L and this is R. R is not equal to L for conical pendulum. That is why we took a sine of this angle theta and then concluded that sine theta is equal to R over L, meaning R is not equal to L. So please take note of this. Is that okay?
Please.
All right.
Yes, please.
So I'm sure you can easily calculate for T, the tension, and then the linear speed after obtaining theta. All right. Okay, let's look at another aspect, please. Let me, conical pendulum falls under uniform velocity motion. It falls under uniform velocity motion because while the object rotates in that conical manner, wherever the object is placed, velocity, acceleration due to gravity's effects at this point are the same. So it doesn't vary the speed of the body. So this conical pendulum falls under uniform velocity motion. Falls under uniform velocity motion because the effect of gravity on the body as it rotates or revolves is the same at all positions. Okay. Carl, mute yourself. Carl. Carl Yodu. Today I want to finish circular motion so that next
Mr.
week
Yeah.
hello.
So do you mean there's no sure way to get the answer?
Priscilla,
Mr. Yeah.
are you talking?
Yes, please.
Then let's dialogue.
Mr. Yeah, please. I was like, so there's no short way possible to get the
Is that
answer.
short way?
Yes.
To do this?
Yes, please.
Oh, Priscilla, what short way again do you want? This is, you see, just spend time and go through whatever you've done. You master, okay? Are you okay? That's the short way. If you use formulas, it will work, but it will be a problem when you don't memorize the formula. And I wouldn't encourage such a style of learning. Okay. The next thing I want us to look at is vertical oscillation or vertical circling. We've done horizontal circling. One of the, you see, under the horizontal one, we've learned about when an object is tied to a string and whirled at 0 angle. Objects tied to a string and whirled. Here, the angle the string makes with the horizontal is 0. So this is an example of horizontal oscillation or circling or revolution. Then 2, conical pendulum is another form of horizontal revolution. So in the first one, as I demonstrated, we have this when the object revolves along the horizontal plane, the horizontal. Conical pendulum, where theta is angle is involved and the object revolves and cuts the shape of a cone. For vertical oscillation or revolution, this is what we have. Watch the demonstration. This time, the object moves along the vertical plane, up, down. So this is how that revolution is. So this object is moving. The board is a vertical plane. So look at it. The revolution is like this. Along the vertical. Okay. Revolution and application of this is merry-go-round, the roller coaster. So that is a practical application of vertical revolution, where the object revolves along the vertical plane. Please, are you okay? Are we okay with that?
Yes. Yes.
So the roller coaster is an example of, or the merry-go-round is an example of vertical oscillation.
Yes.
So vertical oscillation, or instead of oscillation, let me call it revolution. So here, the object revolves. My circle is not circling enough. The object revolves along the vertical plane. So at one point, the object is here. Another point, the object is here. Another point, the object is here and here. Okay, in that anti-clockwise rotational manner. Okay, and here, let's consider a situation of if it is moving at that uniform speed, what happens? Okay, so assuming the body, this is the reference point where it is beginning to move. A, B, C, D. This distance is the length of the string. This is the center O of the circle. Okay, so it means this is the length of the string. Assuming the body starts and then comes to this point. So it has moved from point A to point B. And as it moved, it is covering an angle theta. So A, let me clear B. It is now over here. It has moved from A to a point B. And this angle here is theta. This is a string. The string has a tension in it. The tension is always directed to the fixed point where it is kept in position. So if I'm the one handling, the tension is directed to my hand. So this is T. This is the weight of the sphere, mg, the point B. Now, if I extend this tension vector, I have this angle corresponding with this angle. Or another way to do the same thing is that if I extend the weight vector, I have this angle alternating with this. So if this is theta, this is also theta. And by vertically opposite angle rule, this angle is also equal to this. So either you pick it using alternate angle or corresponding angle approach. Please, are we okay?
Mr. Jack.
Hello.
Mr. Jack, please, the second triangle you drew, please, would the line touch the circle at B?
Oh, this is not a rect. I'm just extending the weight vector in the opposite. I'm not drawing it to touch this one, no.
Okay.
So I have this as a weight and then an angle of tilt theta. Now, what is the adjacent? The adjacent of a right angle triangle is that side of it which is just close to the angle. So if we look at this angle theta, if I want to measure the magnitude of this angle, how would I measure it? I'll place my protractor 0 point or 90 point here and make sure that the horizontal lies here. And then we'll read from 0 up in this direction to determine this angle theta. So it means that if I draw a horizontal line beside the angle, this side becomes an adjacent. Adjacent because it is the reference line for measuring the angle. If you are measuring this angle theta, you reference it from this line. This is where the horizontal line of the protractor, it will lie on this line, and then you read it this way to get theta. So this extended line is drawn. Now, when I draw a perpendicular line from this extended line, I have the opposite to the angle. So get the reference line, which will enable you measure this angle. And when you draw a perpendicular line from that line, you have the opposite to the angle. So we have formed a right angle triangle. This is one side, MG. The angle is theta. Now, when you draw this line, which would help you measure the magnitude of this line, angle, along this line, we have the adjacent. So when you measure a perpendicular line from this line, you have the opposite. So we have a right angle triangle, this side to be the hypotenuse, adjacent, and then the opposite. The hypotenuse is MT. The angle is theta. Now I want us to resolve to get the adjacent and to get the opposite. Are we okay? Hello, are we okay?
Yes, please.
Okay, so let's resolve to get this component and then this component. For anytime we need adjacent, the trig ratio which comes to mind is cos. Cos theta is equal to the adjacent, which we don't know, over the hypotenuse, which is mg. Therefore, the adjacent is equal to mg cos theta. So this component we will call as mg cos theta. It's obvious the opposite would also be mg sine theta. So we have resolved. Let me clear this side to make it clear. There is the weight mg. When we extend this line, we have an angle of tilt theta. By resolution, we realize this part is mg cos theta, and the opposite, which is perpendicular to the adjacent, is also mg sine theta. We are creating something for whatever we are analyzing. Now, when we look at the forces acting on the body, okay, we realize that we have this direction, we have T. This direction, we have mg cos theta. Okay, and we are only looking at this because of the fact that this is moving in a circular path, and in circular motion, the force which enables it to stay within a circular path is centripetal force, and this is always directed to the center. So on the body, we are not considering the weight, neither are we considering this because these forces are never directing to the center. We are seeing this force, these forces, okay, which can have a direction towards the center. There is a force here, there's another force here, all acting on the body. So there will be a net force. What is the net force? The net force between T and mg cos theta must be T minus mg cos theta. It cannot be mg cos theta minus T, because when this component is greater than the tension, the strength would break and the object will fail to stay within the circular path, because it's like hanging you on a thread and your weight is greater than the tension within the thread. Because this is greater, the thread will just break and you fall. So mg cos theta cannot be greater than T, else the body will not be able to stay within the circular path. It is T that must be greater than mg cos theta to give you the net. Please, am I clear here?
Yes, please.
So,
Please, Mr. Dia,
hello.
please, you said the net force to be given if T is greater than mg cos theta, right?
So, yes, so there is a net force. The net force must be equal to T minus mg cos theta, and not mg cos theta greater than T, because if this is greater than T, the thread or the string would tear apart and the object will fail to stay within the circular path. Moreover, the net force is what provides the centripetal force. And the net force is also in the direction of the greater force. So imagine this is greater. When you subtract T from this, the net will be mg cos theta minus T. And the net will be in the direction of the larger force. Meanwhile, this object, to stay within the circular path, the net force must be directed towards the center. The reason for which T must be greater than mg cos theta. All right.
Yes, please.
All right. So because the net force always follows the direction of the larger force, always follows the direction of the larger force, the net force is therefore directed towards the center. And if a force is directed towards the center, then that force is equal to the centripetal force. So we
Sir.
equate, hello,
You said the net force always follows
the direction of the larger force. So because
Okay.
T is greater than mg cos theta, this net force, which is T minus this, would have a direction towards the center, because T is to the center of the circle, O. And I've indicated the center of the circle to be O. Please, are you okay? So it
Yes,
means
sir.
that the centripetal force is equal to the net force. Therefore, mv squared over r is equal to t minus mg cos theta, or m omega squared r is equal to t minus mg cos theta. So this is the general relation we'll be using to analyze as the object moves vertically or revolves vertically. So if you are clear with this part, then you are good, or we are good to go. Pay attention and let's quickly finish this. Can I adjust the screen?
Yes, please.
Today I'm bent on finishing circular motion. Now, as the body rotates, as the body rotates vertically, what happens is that the tension within the string at different points, A, B, C, D, changes. So as the object rotates vertically, as the body rotates vertically, the tension within the string at different positions also the tension within the string at different positions also changes. Chris, are you there?
Yes, please.
Okay. So if the body moves from the starting point, the reference point, and then move from A to B. So at B, what is the tension in the string? We'll use mv squared over r is equal to t minus mg cos theta. Now, when the body moves from A to B, what angle has the body covered?
90.
90. So when the body moves from A to B, theta is equal to 90 degrees. So if theta is 90, when you substitute it into the equation, you have T equal to mv squared over r, meaning that at B, the tension within the string T is equal to the centripetal force. At C, when it moves from A to C, what is the angle covered?
180.
180. So theta is equal to 180. Therefore, mv squared over r is equal to t minus mg cos 180 degrees. Cos 180 is -1. So we have T plus mg. Yes, just T plus mg. Therefore, T is equal to mv squared over r minus mg. So when the body moves from down here, A to C, this is the expression for the tension in the string. Now, the tension in the string at points B and D are the same because gravity, effect of gravity at this level is the same. But you can also try, please. So when it moves from A to D, what's the angle involved? What's the angle involved?
90.
But what's the angle involved?
90.
A 90, right? It's moving from A to D.
D. So is it clockwise or anti-clockwise?
We are moving anti-clockwise.
270.
So theta is 270. So put that into the equation and then tell me the equation of, or the expression for T. Yes, what did you make for T?
MV squared over R.
Good. So I earlier told you that because points B and D are the same level, the tension within the string at both points are also the same. D. So B and D have the same tension within the string. The reason for which you are also having T to be equal to mv squared. Now, when the body rotates and then comes back to where it started, theta, so at A, theta is equal to 360. So when theta is 360, what will be the expression for the tension, T? Do that for me. Inshira ba adampa. Inshira. Inshira. Oh, she's not the one. Yes. About what did you make?
The tension is equal to mv squared over r plus mg.
Good. I'm coming. So, yes, T, the tension T at this point is equal to mv squared over r plus mg. Now, look through the 4 positions. Whatever we got for the 4 positions, A, B, C, and D. Tell me where we can have maximum tension in a string and minimum tension within the string. Where can we have maximum tension in a string? And where can we also have minimum tension within the string. Think through. I need the maximum and then the minimum. If you are ready, share with us. Where do we have maximum tension? Where do we have minimum tension within the string? Is anybody ready? Maximum tension and minimum tension. Okay, Lizzie, share what you have observed with us. Lizzie? Oh, Lizzie is not ready. Okay, Amma.
So please, I think at a at so you've moved the I can't see the down of the word. Okay.
Okay.
I think at C tension will be minimum, and at A tension will be maximum.
That at what?
At A, where to attain 360 degrees, tension will be maximum. But at C, where it will attain 180 degrees, tension will be minimum.
Good. That is it. So when an object is in vertical revolution, we say that, look at the diagram. Maximum tension occurs in the string when the object is below. So this point would give you a point of maximum tension. When the object revolves and it comes below the vertical circle, then up the circle, minimum tension occurs there. And so look at the expression for T. This T at A gives us T maximum. So T maximum is equal to mv squared over r plus mg. Okay, and T minimum occurs above the circle. This is the expression for T minimum. Minimum tension occurs above the circle. And these are what will be asked. Calculate the maximum tension in the string. Calculate the minimum tension in the string. And please do not overlook the fact that this can also, the centripetal force can also be expressed as m omega squared r. M omega squared r. And 2, in some other books, Atake and those books, you also realize that the same formula or expression, T minimum, is expressed as M out V squared over R minus G. And T maximum is equal to M out V squared over R plus G. It's just a substitution of the common m. Okay. As I said, the centripetal force can also be expressed as m omega squared. So these are the key details of what we are doing. Please, any question?
Mr. Adria.
Hello, Amma.
Mr. Adria, please, I was wondering why tension will be less at the C part. Is it because of gravity?
It's because of gravity. The
Okay.
effect of gravity at this point, okay, is greater than at this point. Don't forget, potential energy is mgh. So as h increases from the surface of the earth, you realize that potential energy also increases. So the potential energy of the objects here and objects here are different. The reason for which there is a change in the tension.
So, sir, please, at C, is centripetal force 0?
At
At
no,
C, where do you see it maximum?
no, at C, we said if you make centripetal force, you see the object is within a circular path, even though the revolution is vertical, meaning there is centripetal force here at all the points. The reason for which it can. So at C, to determine the centripetal force, just make mv squared the subject, and it will give you the centripetal force there.
Sir, please, when we make centripetal force the subject, it will become greater than tension.
How do
Doesn't
you
it give
know?
it?
How do you know?
Sir, but tension will be centripetal force will be equal to tension plus weight.
It's even here. At C, this is mv squared. It's equal to T minus mg cos of the angle, the 180. So this is what you are talking about.
Oh,
Okay. This same thing is also explained differently. You see, from what we are doing, no matter the angle given, you can also calculate the tension there. If theta is 30, 60, 45, the same thing is explained in Atake and other books in this way. Let me quickly discuss that with you. It's simple. That is simpler. But this has a further important application than it. So in what is within the books, they only consider the tension within the string at this point and at this point. Below and above. Now below, the object's weight, the weight of the object, which direction will be the weight of the object? At A, B. Please, which direction will be the weight of the object? Will it be up or down?
Down.
So the weight would act here. The tension in the string is always directed towards the center, the fixed point where the body, okay, the axis of rotation, where the rotation actually takes place. And when the object is above it, which direction will be the weight of the object? Which direction will be the weight? I mean above.
Downwards.
So weight always follows the direction of gravity. Down. Mg. The tension within the string is always directed towards the center. So at A, we have two forces, one acting downwards and the other one acting upward at A on the body. What will be the net force? The net force is the difference between them. Now, if mg is greater than t, the object tears apart, fails to stay within the circular path. So once it is expected to oscillate vertically, then t must be greater than mg. Therefore, the net will be t minus mg. And the direction of the net force always takes the direction of the larger force, T. And because the net force is directed towards the center, mv squared over r is equal to T minus mg. So that is another way of obtaining the same relation. At B, what happens? At B, the net force, all the two forces are acting along the same direction towards the center. So net force is equal to mg plus t. And the direction of the net force is the direction of the centripetal force. So mv squared over r is equal to mg plus t. Therefore, t is equal to mv squared over r minus mg. And over here, t is equal to mv squared over r plus mg. So this is another way to obtain the same relation. But the disadvantage is that here we are only considering two positions, below and above. And it looks as if here we are also only considering when it is 0 and when it is 180. But when you are given anything in between, theta is this. How do you determine it? The reason for which this one is superior to this one, to this second method. Please, are we okay?
Yes.
All right. Quickly, let's apply it in solving problem before we
Miss
look
Pedia,
at. Hello.
please can you move your camera down a bit?
Is it okay?
Thank you. Yes, please.
Okay, so let's put down this question. An object of mass 8.0 kilogram is whirled round rapidly, whirled round rapidly in a vertical circle. This adjective description very important. In a vertical circle to mean to explain to you that we are looking at vertical revolution. It's whirled round rapidly in a vertical circle of radius 2 meters with a constant speed of 6 meters per second. with a constant speed of 6 meters per second. Calculate the maximum and minimum tensions in the string. Calculate the maximum and minimum tensions in a string or in a string. Take G to be equal to 10 meters per second squared. So you have to calculate the maximum and minimum tension in the string. Take G to be equal to 10 meters per second squared. Make me proud. If you are somebody, a fan of Formula One and MotoGP, the MotoGP is for motorcycles. Formula One is for cars, okay, races. When the MotoGP people, whenever they are, okay, emotion, and then they want to bend, negotiate a curve. You know, you are in a competition. So if you want to negotiate the curve, you can slow down to 10. By the time you finish, somebody has overtaken you. So they still move at a top speed, but to ensure that they are able to turn with that speed, they tilt the motor as if they are falling. Please, have you seen watched that on TV before?
Yes, please.
So to be able to, the point is that if you want to turn safely, the advice is slow down and turn. But this is a competition. It isn't Yachra and Ekuyadoma who are riding for you to just slow down and go. It's a competition. So you can't slow down and turn. And so to be able to, make that turn and still maintain the speed, then you need to employ some skills. Tilt the motor as if you and the motor are falling down. Okay. And what they are doing is that They want their natural body, the body of the motor and the rider, to provide that extra centripetal force which will enable him turn, because he cannot depend on friction. Friction depends on the nature of the surface and the speed. But the speed is great, so you need extra turn to help you make the turn. The reason for which they make that turn, so that they will have that extra turn, which will enable them still make the turn. Now, in the case of cars, MotoGP, this car races, whenever they are in competition and they want to turn, this time you can't tilt the car and yourself as done by the motor riders. As for car, you can't tilt it unless the rider and the car are for cartoons. Okay. So for cars, because the drivers cannot tilt the car to make that turn, the road must be built, okay, to support them. So the Formula One, the heavy road they use, it is designed differently so that while they move with that top speed, they can be able to make that turn without skidding. And this is what it is termed as banking of roads. So what is banking of roads? Banking of road is an architectural design. Let me give. So banking of road is an architectural design where roads are built in such a way that it is tilted at an angle towards the center of the road. So it's an architectural design where roads are built in such a way that it is tilted at an angle towards the center of the circle or of the road. Okay. Now the rationale behind building roads in this manner, one. So rationale behind the banking of roads. One, to prevent skidding of vehicles, meaning it is for safety, for safety reasons. And two, it enables motorists or road users to move or speed at a certain maximum, allowable speed. It helps them to travel at a certain maximum allowable speed. But the point is that this speed cannot be moved with if the road is not banned. So the moment the road is banned, drivers or motorists have that freedom to move at a certain speed, which can never be moved with when the road is not banned. Please, are you there? Hello, are you there? Okay. Can I adjust the screen so we can continue? Charlotte. Charlotte. Okay, maybe she's gone. All right, so let's look at how the difference between a banked road and an unbanked road. So for an unbanked road, that's the usual circular roads we have around. The road is circular. It is not tilted towards any angle. So for unbanked, there is no angle. Now, when it is banked, I'm just drawing the outer edge. The road is built in such a way that the upper end of the road is raised. So this side is raised and tilted towards a certain angle, theta, towards the center. So the curvy road is like this. Now, when drivers are moving on such a road, you realize that I think the banking angle is too much. When drivers move on such a road, the car also seems tilted. This is a car. And the car is tilted as if the car moves along an inclined plane. Okay, but when the road is unbanked, it's just like, let me draw the outer edge. There's a certain portion of the road. The car is not tilted. So this is unbanked, this is banked. So the road is designed in such a way that the upper end, the outer edge is tilted, raised, and turned through an angle theta towards the center. And if the road is built in this manner, it's the same as the Formula One driver who has to bend like this so that he can turn. And in fact, whenever a road is banked, drivers can be able to make a turn safely without depending on friction. Well, let's add that information too. whenever a road is banked, drivers can able to move freely without depending on friction. Don't forget that for an unbanked road, unbanked road, frictional force between the road and the tires provide the centripetal force. Centripetal force. Now, when roads are banked, motorists can make the turn without depending on friction. So that's the difference. And this idea of banking is actually involved in road construction because you see outside during winter periods, the road surface is snowy. So in some areas, snows fill the surface of the road, reducing friction to very, very minimal. And if friction is minimal, centripetal force, okay, is also minimal. If friction is minimal, centripetal force will be minimal. So at curvy roads, they deliberately bank the road so that there wouldn't be that reliance or dependency on friction to make a turn. In our part of the world, every day there will be friction because there wouldn't be any snow. So in our case, when the road is banked, we depend on the banking angle and also depend on friction. But outside, because of their snowy weather conditions, some curvy roads are banked so that motorists or drivers will not depend on friction to make a turn. Once the road is banked, you can easily make that turn. That's okay. So, Is there any question? Okay, so what we will do is that in our next discussion, we'll go into when the road is banked, what provides that extra centripetal, what provides the centripetal force. We are saying that when the road is banked, drivers do not rely on friction to make that turn. So what is that thing which provides, I think it should be, the other one must be, what is that thing which provides the centripetal force? That is what we'll be looking at in our next meeting, which will certainly be on Monday. I think Monday we need to finish this and then start with SHM or lights. Okay, so this is a car on a banked road. The banking angle, the road is tilted at an angle theta. what happens. So we'll continue this and finish on Monday. Okay. But as usual, you'll have 1 or 2 assignments to engage you during the weekend. Please take care of yourselves and go to the site, the YouTube channel. Please subscribe, watch, and send a beautiful comment to me. So until we meet again, possibly same time, next week, Monday, may God be with you. And in fact, continue revising. Bye-bye to all of you.
Bye. Mr. Edia, please wait.
Edia,
Yeah, please, can you shoot the camera too?
Dada,
Like you explain there. Down.
Dada.
Yes, so much. Thank you.
Okay. All right. So, Charlotte, my earpiece is going off, so
Yes.
I'm charging it. When you finish, turn the laptop off yourself.
Yes, please. Mr. Edia.
Charlotte, are you done?
Yes, please.
Eh?
Yes, please. Please, can you hear me? Mr. Edia, please, you are still recording.
Charlotte. Hello, do I turn it off?
Yes, please. Please, can you
Yeah,
hear
you are
me?
here. And
Please, you can turn it off. You are still recording. Oh, good.